we'll now discuss another source of functors that is useful in many contexts and that works for general category. So if C is a category and B is an object in C, then we can define the following two functors. We get a functor that's usually denoted by C, B, comma, blank, and that's a functor from C to the category of sets. And on objects, it's defined by sending an object C of our category to the set of morphisms in C from B to C, and it sends a morphism from C to C prime to the morphism between these homomorphisms, between these morphism sets that given by post-composition with the morphism C. So given a morphism from B to C, we can compose with C to C prime to get a morphism from B to C prime. And it follows from the associativity of the composition law in the category that this is indeed a functor. And it's this type of functor is called a representable functor, and it's a functor represented by B. And there's something analogous that happens if we put the B in the second variable, and this time we get a contravariant functor that's denoted by C blank comma B, and this is now the functor from C to the category of sets that sends an object A to the set of morphisms from A to B in the category C. And again, we have to say what it does on morphisms. Well, if we have a morphism G from A to A prime in the category C, then we send it to the pre-composition with G. And this defines us a map that goes from the set of morphisms from A prime to B to the set of morphisms from A to B. Because we have a morphism from A prime to B, and we precompose it with a morphism from A to A prime, then this gives us a morphism from A to B. And so this is indeed a contravariant functor. So I will now come to the last general definition about categories that comes up in many contexts, and this is a notion that relates to functors, and the definition is that of a natural transformation. So let f from C to D and G from C to D be two functors, then a natural transformation alpha from F to G, so natural transformation from F to G, this is a collection of maps alpha A from F of A to G of A. These are maps in D, and we require to have such a map alpha A for all objects A in our category C. And now we require a compatibility with the composition that works as follows. So we require that for all morphisms f from A to B in C, the following square commutes. So what we can do is the following. We can start from f of A, apply the functor f to the morphism f. So this is a capital F applied to lowercase f. This brings us to f of B. And then we can apply the map alpha B to get to G of B. So this alpha B is part of the data of our natural transformation. Or we can do it the other way around. We can first apply alpha A to get to G of A, and then apply G to the map F in C. And so this gives us two different ways to get from F of A to G of B, and we call this collection of maps a natural transformation if this square always commutes. So meaning that we always have that the composite of G of F with alpha A equals the composite of alpha B and F of F. So although this looks like something rather complicated, it appears to be in fact the case that historically the notion of a natural transformation predates that of a functor and that of a category. So this is a mathematical structure that people observed in examples, and then they tried to make this a general definition, and this required people to say what a functor is, and it required people also to say what a category is. So it's really the central definition in the subject. Maybe one addition to the definition, we say that a natural transformation alpha is a natural isomorphism if this morphism alpha A is an isomorphism in the category D for all objects A. So I'll start with a basic definition of a natural transformation. This brings us back to the example of a category that we built from a group. So if G is a group, then we form this category script G, which was the one object category associated to this group. It had the set of homomorphisms from the only object to itself were just the group with this composition law. So in this case, one can easily check from the definition that a functor from this category G script to sets, that's the same as a G set. So a set with an action of the group G. And if we now have two such functors, then a natural transformation of two such functors from G to the category sets, this is the same as G equivariant map of G sets. And here equivariant means it's a map of the underlying sets that commutes with the action of the group on X and Y. So this is a simple example of natural transformation. A less simple example of a natural transformation is the following. I discussed that the dual vector space construction provides a functor from the category of k vector space to itself. So this is a contravariant functor. If we apply it twice, it becomes covariant again, because reversing arrows twice means we don't reverse any arrows. So we can consider the functor double dual, which I denote like this, and it turns out that there's a canonical natural transformation from the identity functor to the double dual of the vector space. So canonical natural transformation from identity to the double dual, and it's one of the maybe somewhat surprising and also somewhat more involved facts about linear algebra, that this here happens to be a natural transformation if we restrict it to finite dimensional vector spaces, but for a general vector space of possibly infinite dimension, it will in general not be an isomorphism. So this is a non-trivial example of natural transformation. I'll give another non-trivial example of a natural transformation. Among the examples for functors, we saw that the n times n matrices can be viewed as a functor from commutative rings to monoids, and now it's important that I say monoids. But there's of course also the forgetful functor from commutative rings to monoids. So this is a functor that only remembers the multiplication, and now one can check that the determinant is a natural transformation whose value at a commutative ring R, well, it's just the ordinary determinant of an n times n matrix with entries in a ring R, viewed as a map from the set of n times n matrices to the underlying monoid of the ring R. And this is an example that enlightening in the sense that this is just a one-sentence statement, and if one now unpacks all the definitions that are involved here, one can fill quite some paper or blackboard with the meaning of all this. And so this is an example for why this is an efficient language to encode mathematical statements. So the last question I would like to address is the question of when we view two categories as being the same. This question has a pretty obvious answer, so I introduced the notion of a functor, and I explained that two functors can be composed, and so it's then easy to define isomorphism of categories as a functor that has an inverse, so that functor in the other direction, so that both composites are the identity functors. That's a tempting definition, but it turns out that this definition is not so useful in many of the examples. So it turns out that this would exclude many interesting examples, And it also turns out that in practice, somewhat weaker definition turns out to be way more useful. This, the definition I'm giving now, we say that a functor f from C to D is an equivalence of categories if there exists a functor G from D to C in the other direction, and natural isomorphisms eta from the identity of C to the composite of G and F, and epsilon from the composite of F and G. So this is an this is a functor from the category D to itself, and we require that there is a natural isomorphism to the identity of D. And as I already said in words, we do intentionally not require that GF equals the identity on C and that the other composite FG equals the identity of D. So we only make this weaker requirement here. I now give a criterion that allows to identify natural, allows to identify such equivalences of categories, and that's often convenient to check in practice. For this, I need a little bit more terminology. So let F from C to D be a functor, then we say the following, then F is said to be full if the induced maps, so for all objects A, B in C, the induced map on morphism sets from CAB to D, F of A, F of B is surjective. So we should note that it's not necessary to start talking about epic at this stage, simply because this is just a map of sets, so this is doesn't require any fancier notation. So we say that this functor is faithful if an analogous statement holds, namely if this is an injective map. So in particular, functor is full and faithful if and only if it induces a bijection on morphism sets for every pair of objects A and B. And lastly, we say that such a functor is essentially surjective if the following holds: if for all objects D in the category D, there exists object C in the category C and an isomorphism from F of C to D. So this last condition refers to what the functor does on objects, and it says that up to isomorphism, every object is in the image of the functor. So every object in D is isomorphic to some object in the image of the functor C, while these first two conditions were referring to what a functor does on morphisms. So here now comes the theorem that identifies equivalences of categories. A functor f from C to D is an equivalence of categories if and only if f is full, faithful, and essentially surjective. So in other words, having these three properties characterizes the equivalences of categories. I will not present the proof of this theorem. It's very advisable to try to prove this just from the definitions, which is possible. One should maybe note that it needs the axiom of choice, but this we don't worry about. Good reference for the proof, including, I think, all its details, is theorem 1.5.9 in Emily Reel's book, Category Theory in Context. I'll now end with an example of an equivalence of categories, which should be familiar. So let K again be a field, and we now let K vect Fd be the category of finite dimensional K vector spaces. So the objects are finite dimensional K vector spaces, and the morphisms are again linear map of K vector spaces, but it's a smaller category than the category K vect that we considered before, simply because we not allow vector spaces of infinite dimension. So the other category I'd like to consider is the category net K that are now defined. So this is a category with objects, the natural numbers. So the set of objects is a set of natural numbers, and we define the morphisms from M to N be the set of N times M matrices over our field K, and the composition in this category is just the ordinary matrix multiplication and the identity morphisms are, of course, the usual identity matrices. And now the observation is that we get an equivalence of categories that goes from this category of matrices to the category of finite dimensional K vector spaces. Well, it's defined on objects by sending a natural number M to the standard K vector space of dimension M, the K to the M, and when we have an N times N matrix over K that's denoted by A, well, then we send it to the linear map that is given by multiplication with this matrix. And I claim that this is an equivalence of categories. Well, in some sense, this is one of the main results of a linear algebra course. Well, it says that, so the essentially surjective requirement of this used in this theorem that we apply for this purpose. This says that every finite dimensional vector space is isomorphic to some vector space of the form Km. Well, this is something we know. And we also know that the linear maps between these standard K vector spaces correspond to matrices via a one-to-one correspondence. And this exactly says that in this example, this map here is both injective and surjective. And what we also learned from this example is that with equivalences of categories, it's often easy to write down the functor in one direction, while the inverse might be difficult to describe and depend on choices. So to get an inverse here, we have to choose isomorphism. So this is more complicated, but this is why it is convenient to have this theorem that identifies an equivalence of categories just in terms of properties of the functor pointing in one direction. Okay, I'll stop here.